All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandrea, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on the possibilities for planetary science and astrophysics. And after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentation, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. The members of today's panel are all from the Interstellar Probe Study team and are Pontus Brandt, the project scientist, Kirby Runyon, the planetary science lead, Abigail Rymer, the exoplanet science lead, and Casey Lisse, the astrophysics lead. And with that, Pontus, the virtual floor is yours.
Thank you, James. Hi, everyone out there, and welcome to another webinar. I'm going to spend my usual 5 minutes of introduction for those of you who do not know what the Interstellar Probe concept is about and what we're doing. So before I give the word to our speakers today, I'm going to give you a quick background. And this is a current study that is being conducted for the NASA Heliophysics division. We started this study now over 2 years ago. It is a trade study focusing on a pragmatic mission concept using technology that is ready for launch in the 2030 with a nominal lifetime of about 50 years and the ability to operate far beyond where the Voyager have brought us today. So over the past 2 years, we've seen an incredible amount of momentum across the international science community. And we have now over 250 scientists and engineers that are engaged. You can see the photo here on my first slide from the workshop that we held over a year ago now. And the participation is from more than 9 countries, and they are actively following or are engaged in this study. So if you're interested, please email me, James Mastandrea, or go to the website, and we can you can enlist in the email list. Next slide, please. All right, so what is all of this about? So our entire solar system is encased in a bubble. It's a magnetic bubble that we call the heliosphere, and that is carved out by the solar wind as the sun plows through the unknown interstellar medium out there, which is built up of all the gas from all the remnants of exploding stars and supernovas throughout the galaxy. And ever since the dawn of the space age, scientists have discussed sending a probe that will be leaving the sun's gravity well and go beyond our heliosphere into that unexplored interstellar space. So the major science goals of such a probe, such an interstellar probe, haven't really changed over the decades. The primary goal revolves around exploring the boundaries of our heliosphere and to determine the properties of the surrounding interstellar cloud and the galactic environment that our star, the sun, sits in, and all the other stars around it as well. So as such, an interstellar probe, and that's why it's so exciting, really represents humanity's first step into galactic space. Of course, it has a very unique trajectory. It goes through the outer solar system, so that also presents opportunities for planetary science and even astrophysics. And those possible goals are what the speakers are going to introduce today. Next slide, please, James. So to give you a sense of the enormous distances here, as usual, showing the map, as we call it. We've laid out the solar system, the heliospheric boundary, and the immediate interstellar neighborhood, of course, on a logarithmic scale, because we wouldn't be able to fit it on a linear scale. I have pointed out Voyager 1 and 2 here that are the accidental interstellar explorers. They're now about 150 and 124 AU. From the sun, and they will likely have power for about 5 more years, and will thus have brought us to the mere doorstep of interstellar space for the first time. The probe, the interstellar probe concept we are talking about is, of course, not going to Alpha Centauri. It is a pragmatic concept and would be a large strategic mission or flagship mission, as people have called it before. The study focuses on mission architectures and technologies that I said are ready by 2030 and have the ability to operate at 1000 AU and have conventional RTG power of about 600 watts at the beginning of mission and a nominal lifetime of 50 years. So multiple studies, as I alluded to, have been conducted in the past, of course, but always we come back to that the technical hurdle is propulsion. But now it looks like with the availability of large launch vehicles, we've overcome that hurdle. And that's why this is becoming more urgent and realistic. So using an SLS Block 2 and the Jupiter gravity assist, you already achieve asymptotic speeds that would bring a probe to the boundary at 90 AU in a mere 12 years. And for the purposes of today's talk, it would bring us to a first possible KBO flyby in only 6 years. So this brings me to today's talks. Next slide, James. So first off, we have Dr. Kirby Runyon. He will talk about KBOs and dwarf planets as the fossils of solar system formation. And then Dr. Abby Rymer will talk to us about what we can learn by going outside and looking back at our solar system, just like the Voyagers did, to see how that can teach us on exoplanetary analogues that would inform perhaps other exoplanetary studies out there. And lastly, Dr. Casey Lisse, he will talk to us about how we can get a look at our unseen circumsolar dust disk and how that unlocks the secrets of planetary system formation, and how traveling beyond it opens up also the window to understanding early galaxy formation. So with that, engage, and I'd be happy to take you on a journey through the outer solar system. Thank you.
All right, well, thank you, Pontus. I'm really excited to be presenting to you something I'm really passionate about, and that is being able to do comparative planetology of Kuiper belt worlds enabled by the near-term interstellar probe. And as I hope you'll see, really it's the dwarf planets from a planetary science perspective that really beckon in our solar system. Next slide, please. So of the different types of planets in the solar system, we have a handful of terrestrial planets, we have a handful of giant planets, but we have more than several handfuls of dwarf planets. Dwarf planets are overwhelmingly the most common type of planet in our solar system, and yet they're really the least explored. We've had so few missions to go explore them, and they can tell us so much about solar system evolution, its current state, and even begin to answer questions about habitability and astrobiology. And so there's really this strong impetus. If you're the type of explorer that wants to see beyond the next hill, this is really the regime where we need to be focusing on. Next slide, please. So to date, we have only explored 3 Kuiper belt dwarf planets, using the term a little broadly here. Triton in 1989 by Voyager 2, and Pluto and its dwarf planet satellite Charon in 2015 by New Horizons. And they are all similar in size, although not exactly. Triton is about twice as massive as Pluto. There are similar compositions across Triton and Pluto, but they manifest in vastly different landforms, as we'll see. And Charon, about half the size of Pluto, is a typical size for many of the other dwarf planets. And as we'll see later in this talk, a few other dwarf planets really stand out as really beckoning for potential exploration by a potential interstellar probe, and those are Quaoar and Gonggong. Next slide, please. So as I alluded to in the previous slide, even despite similar compositional similarities between Triton and Pluto, there's really vast differences in the geology, geophysics, and composition across these small planets. If we look at Charon on the upper left, it looks as if perhaps a giant iceberg was partially embayed by a freezing hemispheric surface ocean that quickly froze, potentially after a large impact. There's ice fractures throughout its surface, and it's got a pockmarked cratered surface. Triton there in the middle potentially has spreading ridges indicative of potentially a subsurface ocean. There are sublimational cliffs across the surface seen here, and we also see the soot deposited from geysers erupting sooty material high into Triton's thin atmosphere from the subsurface. Of course, moving over to Pluto, we have a vastly different terrain of a giant convecting nitrogen ice glacier, Sputnik Planitia, where the planet is encircled with a dark, sooty Cthulhu macula, potentially from tholins photolyzed from the atmosphere depositing on the surface. We've also got a lightly cratered surface and grabens extending across, potentially also cryovolcanoes on the far right, seen to rise into Pluto's blue ethereal atmosphere. Along the bottom left, in a paper by Mike Brown, we see where the volatile contents of different dwarf planets are plotted, where the equivalent temperature and the stability of volatiles are plotted relative to the diameter. And the largest handful of dwarf planets seem to retain volatiles pretty well. Charon is relatively volatile depleted, and it's mainly got a water ice surface there. And these other dwarf planets, Quaoar and Gong, its designation was 2007 OR10 until it was officially named Gong, is right on that stability line between volatile rich and volatile depleted. And it's a lot of the volatiles that are responsible for the very complex surface geology we see on Pluto. Of course, the Lisse instrument, part of the Ralph instrument on New Horizons, has shown compositions of ices across the surfaces of Pluto and Charon, shown here in this paper by Will Grundy and others. And taken together, the shape of Pluto, the orientation of fractures across its surface, has hinted at the possible existence, very likely existence, of a subsurface liquid water ocean persisting to the present day. So Pluto is very likely an ocean world, and if Pluto is likely an ocean world, it's possible that other dwarf planets started off with substantial amounts of water in their interiors. And this view here has been beautifully illustrated by James Keen. Next slide, please. There's also planetesimals, many orders of magnitude more than dwarf planets we have in the outer solar system. These fundamental building blocks, the Lego pieces, if you will, of the Lego sets that are the dwarf planets and even larger planets throughout the solar system. And of course, this beautiful view was synthesized from images taken by New Horizons in 2019. We can also start looking at the compositions of water and possibly methanol and other exotic ices across and organic species across the surfaces of planetesimals. And it could be possible that a future interstellar probe could reconnoiter one of these on its way out of the solar system. Next slide, please. Now, with over 130 dwarf planets and potentially millions of planetesimals, they're everywhere. And interstellar probe, if it becomes a real mission, would primarily be focusing on heliophysics as it leaves the heliosphere and dips its toe into interstellar space. Now, dwarf planets are relatively uniformly distributed across the solar system. This is a plot here of latitude and longitude from the perspective of the sun. And if you could advance the slide, I just want to highlight this particular region, kind of near the edge of the nose of the heliosphere, the kind of the direction the heliosphere is plowing into the interstellar medium, and this where it borders with the waist around a longitude of roughly 330 degrees or so. You'll note that Gong and Quaoar line up in this region. Pluto's not far off. A number of dwarf planets are also in the region. Arakoth is right along here. This is also in the region of this enigmatic high energy ribbon of energetic neutral atoms that has been discovered that maybe that perhaps the heliophysicists on a potential interstellar probe may want to explore. And so a planet that fortuitously lines up with this ribbon could make for a very enticing flyby. Next slide, please. So the big picture I want to leave you with has to do with a lot of comparative planetology and ocean world. Some of these top level issues I really want to verbally highlight is there ongoing plume, cryovolcanic, or tectonic activity on these small planets? What can the variability of landforms and compositions tell us about the evolutionary histories of these worlds? What fraction likely have or once had liquid water on or in their surfaces, and how is this related to a planet's window for habitability? We're pushing the Goldilocks zone, the habitable zone, out many tens of AU away from the sun or potentially other star if we're talking about exoplanetary systems. And we're interested in of course, the more dwarf planets we reconnoiter, the more mature the discipline of comparative planetology among dwarf planets becomes, and our picture of the solar system and of habitability becomes more complete. Next slide, please. Now, by way of instrumentation, it's not hard. Even at the very fast speeds we'd be flying by, well, maybe it's hard, but it's definitely a tractable engineering problem. We could get the kind of science we need using high heritage instruments that have already flown, especially visible and near infrared imaging spectrometers that are sensitive to a wavelength of about 0.4 to 3 microns that can really constrain a lot of the volatiles, ices, and organics on the surfaces of these bodies. Instantaneous fields of view of 5 to 60 microradians per pixel. We know how to do this. Can give us the geologic information and compositional information we need if we fly by a distance of between about 10 and 40,000 kilometers. This image here is an MVIC true color scan of Pluto taken when New Horizons was still about 3 times its distance that it came at closest approach. It took this picture from 35,000 kilometers away, and it got 3 times closer to that distance. And already at this distance, with this camera, which MVIC was not the highest spatial resolution camera on board New Horizons, we're already seeing at a pixel scale of about 1 kilometer per pixel, a little bit better actually. And we can already see the Sputnik Planitia nitrogen ice glacier embaying into craters. We see a glaciated and maybe fluvially dissected terrain. We see sublimation pits, craters. We see grabens. We see sublimation cliffs of methane ice off on the lower right near the terminator. Even if this was the only image we had gotten of Pluto, this would have revolutionized our understanding of that planet. If this was the only image we got of a dwarf planet besides Pluto, it would continue to revolutionize. Fortunately, we got much higher resolution and spectral resolution as well, images of Pluto. And so getting the kind of revolutionary science that we need is eminently doable if a potential interstellar probe were equipped with one of these visible near-infrared imaging spectrometers. Next slide, please. So I just want to leave you with this idea. Let's get more dwarf planets in our rear view mirror, like we got from New Horizons. And I'm proud that this is actually the bumper sticker on my car. Next slide. Now, I do want to plug on October 15th of this year, this fall, mark your calendars, 12:05 p.m. Eastern Daylight Time. We're going to have a webinar series devoted specifically to talking about dwarf planets and KBOs as fossils of solar system evolution. So please stay tuned for that. I'm really excited for that presentation. And I think that, and as Pontus is fond of saying, engage. Next up, Abby Rymer will be speaking on solar system planets as exoplanet analogues.
That was awesome. Thanks, Kirby. All right. Afternoon, everyone. I'm Abby Rymer. I'm coordinating the Exoplanet Working Group for Interstellar Probe. I'm actually a planetary scientist, and as you'll see, most of the focus for the exoplanet aspect of Interstellar Probe is in the context of looking back at our solar system in the context of exoplanet analogues. And at first blush, that might seem like a relatively trivial endeavor, something we might be able to do from a Jupiter spacecraft or even by models from the Earth. But I think, as everyone knows, every single mission, every planetary mission we've ever launched has learned new things about every target that it's visited and things that have surprised us. And so I can guarantee that when we look back at our solar system with our real eyes via our robotic cameras, we're going to be learning something new about how we're currently viewing our exoplanet neighbors and far distant true exoplanets. Next slide, please, James. Thank you. So a few high-level questions is, what does our solar system look like to our nearest extraterrestrial neighbors? So this is the question that we're asking ourselves as we look out into the universe. And what can we understand about what is a habitable planet and what is not a habitable planet based on our observations from our increasingly sophisticated telescopes, and of course soon the James Webb Telescope to be launching, hopefully. We can do this in our own solar system by looking back at planets in the habitable zone in particular to see if we can understand why the two neighboring, almost exactly the size planets of Earth and Venus, one with us and one completely uninhabitable. And I think that that's an enormous driving question for, that could be answered with appropriate instrumentation on an interstellar probe mission, and which obviously isn't particularly under the purview of the Heliophysics Directorate. So it will take some expansion probably of the existing payload on a primarily exon heliophysics mission in order to optimize it for those kind of measurements. And so our hope is that we can attract some, real greenbacks to throw money at this problem, to encourage astrophysics and planetary divisions to support some additional payload that we can actually optimize prior to launch deliberately to make these excellent observations, which I think are very needed in this era of exoplanetary discovery. Next slide, please. So it's not crucial, fortunately, for the sort of science that we're trying to do for the exoplanet analog, which is really depending mostly on the interstellar probe being at a vast distance from the sun, so that we can look back at our planets from a vast distance and understand them with our brilliant in situ measurements in the context of our distant measurements that we're making with our telescopes of the exoplanets. So the direction the interstellar probe will be going out of our solar system is roughly noted by the arrow to the nose there. And the nose means the direction that our solar system is moving into the interstellar medium. So that's actually the shortest distance out, hopefully into the interstellar medium. So it makes sense for the heliophysics observations to get outside of our astrosphere. The only habitable astrosphere that we know as quickly as we can is to go in that nose direction. As a planetary physicist and someone interested in particular in ice giants, I'll note that you can see Uranus and Neptune sort of to the upper left and right on that image, and the colours are showing you where they move through those years that are written across the top. So you can see neither of them are in a good location for us to be going past them with the interstellar probe, although I have mentioned it at several meetings that it would be a great opportunity if it could. But that's unlikely, because really the main goal is to make sure we can look back at the whole heliosphere in its entirety with the interstellar probe platform. But as Kirby's noted, we might have an opportunity to fly past Quasar, and certainly the fact of the ice giants being on the dawn and dusk of the sun, more or less, is good for the angular separation as looking back at the sun. And I say that because you're probably aware that the discovery of exoplanets primarily relies on observing them, or the initial discoveries relied on observing them in transit across their host star. It is something that we've explored and discussed and we could revisit, but at first blush, it seems the simplest thing is to make direct observations of our planets away from the sun. Designing instrumentation, cameras that we'd like to use for observations at places such as Quasar, and also enabling them to be able to look directly at our sun to do a planet in transit is a very, very different science objectives. Whereas designing them and optimizing them to be able to look at our planets when they're on the sides of the sun, so that we're not having to have the sun in the field of view, is a ostensibly simpler endeavor. So it's actually quite an excellent platform with that in mind, which is shown a bit more on the next slide. So here you can see this is the angular separation, sorry, angular size of the planet as seen from the interstellar probe platform on the top plot. And then the bottom plot is showing you the separation between the planet and the sun. So that's basically the season of the planets. If you imagine an orrery of the planets going around the sun, the sine wave is us then going round at the edge, and so the furthest distance from the sun, and then behind the sun and straight in our line of sight is when they're the shortest distance from the sun. So you see that we do our Jupiter flyby, which is also some great opportunities there, and depending when we arrive, there may be several spacecraft also in that system. And if you remember, the New Horizons flyby of Jupiter was really unprecedented. Jupiter's magnetotail stretches out in our solar system as far as Saturn sometimes, and New Horizons just went straight down the tail. It was a really fantastic series of observations. So we might hope to do exactly the same, whilst also looking back at Jupiter with our brilliant cameras, with our interstellar probe flyby of Jupiter. You can see on the bottom plot, the black dashed line is it's kind of a limit. It's called the diffusion limit of what we can observe of the planets. So you see after about 100 AU, some of the planets are starting to dip below that line in the 2.5 in the roughly infrared wavelength. But you can also see we get multiple seasons, and at least one season of all the planets before we extend past 1 AU. And most of the planets are still very easily resolved with an infrared camera much further than that. So it's a potentially very exciting, I imagine you don't have to stare at our planets all the time. If we revisit this observation like once every few weeks, once every few months, I imagine that the 7 to 10 years that it's going to take Interstellar Probe to get to the distances outside the heliosphere, by that time, we'll be looking at movies that have been made with our cameras, seeing our planets go around the sun, a lot like you can see Jupiter's moons go around Jupiter if you're looking at it through a telescope. And this figure is from a very nice white paper written by Sunny Harmon, which has just been submitted to the Astrophysics and Planetary Decadal Survey. So it's written with an educated but non-expert author reader in mind. So I encourage you to go and look that up. All those papers are going to be online soon. Next slide, please. Something I'm particularly interested in and more aligned with my regular day job is magnetic fields. Looking for magnetic fields in exoplanets is very much in its infancy because we tend to become experts in what we can observe. And looking at magnetic fields remotely with telescopes is approximately impossible. But one thing that is possible and is actually increasingly happening with the very large exoplanets is observing the auroral emissions, or things we think are associated with auroral emissions. And so I think that looking back with Interstellar Probe from vast distances to see the same auroral emissions that we're measuring in more detail in situ is going to be enormously informative on how we can determine whether or not an exoplanet has its own magnetic field. It may be the only real diagnostic that we can have is if we can see an aurora at a distant planet. And a way to distinguish it being an aurora versus it being clouds is to look for frequencies that are associated with rotation rates which aren't associated with seasons, which aren't associated with the sensible planetary rotation. And also, and the reason I chose these two figures in particular, you can see the streak on Jupiter on the left, on the far right of the planet. That's the Io, that's Jupiter's moon's Io's footprint on Jupiter. And then on the right-hand side, there's a faint footprint associated with Enceladus at Saturn. Those have a very different frequency to the main auroral frequencies. And so actually we might be able to turn in multiple frequencies, and then we'd really be nailing that had to be coming from an aurora. And if we can, which we really don't know, but if we can convince ourselves that a magnetic field is a requirement for a planet to be habitable, this will be a very important diagnostic. Next slide, please. And we've had some really excellent discussions at the two very excellent Interstellar Probe workshops that we've had in New York the last few years about hypothetical planet X, which is not in my expertise at all, but there's this enormous mass associated with some gravity outside our solar system, and it's being sought after as a hypothetical planet X, as something that might be a Neptune-like sized planet on the edges of our solar system. And if this were confirmed to be the case, I can only imagine that Interstellar Probe might turn into a Planet X discovery mission, which is incredibly exciting and of course very relevant to exoplanet research, adding another data point to the few planets we have available in our backyard. And next slide, please. So finally, my summaries I'm using. So the Interstellar Probe is a fantastic mission as it stands, and it does have a lot of instrumentation that can be doing dual duty for all of the science that we talked about today. But it could specifically provide a terrific platform for exoplanetary science with some augmentations which are made deliberately to the cameras and the payload in terms of our observables, to understand our solar system in terms of, I love the phrase habitable astrosphere, which we've used a lot in the Interstellar Probe community as we've been going forward. Looking back at our solar system in an exoplanetary context, the observation of the pale blue dot, I don't know if it's true, but I hear that was an observation they had to fight for. It was because the science associated with that observation wasn't obvious. Why would we turn our amazing spacecraft to look at a dot in the sky, and yet possibly the most important and influential space photograph ever taken? And what I'm imagining is that we're basically going the footsteps of Voyager, and we're adding the entire solar system and multiple observations of that pale blue dot to humanity's legacy as we go in our search for life in the solar system. So if you'd like to learn more, on the next slide, we have coming up in January 2021, we're going to be talking more about exoplanet analog opportunities in this same webinar slot. And thank you for your attention. I think I'll be handing over to my dear friend and colleague, Casey Lisse, to discuss the astrophysics, moving even further out into our solar system, out into our interstellar medium.
Thank you very much, Abby. And I am privileged to talk to everybody today, thank you for all attending, about the fantastic and transformative science that Interstellar Probe can do by going outside of our solar system, going into the nearby galaxy. We can do things that humanity's never been able to do before. And there's so many things I can talk about, but I'm going to pick two most important ones we can think of. One is getting the first complete picture of the circum-solar dust disk and cloud that is around our solar system. It is the leftovers of planet formation. Abby just talked about how our solar system compares and looks compared to other solar systems. And this is one of the big pieces of that puzzle. The other is that once you're outside that cloud, suddenly you're outside a fog bank and you can see the rest of the universe. And we have the very subtle, very small goal of looking at all the light ever made by all the stars and galaxies in the universe since the beginning of cosmic time. We can measure that in the diffuse background. And from that, we can get a very good handle on how the first stars and galaxies form. So that being said, let's go ahead and talk a little bit more about these subjects. Next slide, please. So as a cartoon, there's a lot here, and I'm just going to go brush stroke very quickly, is that stars form by collapsing molecular clouds. You can see up to the left, it takes about 5 solar masses to make the 1 solar mass star that we live around today. The cloud collapses, makes a disk, which is spinning and rotating, blows out stuff from either end. By the way, the cartoon is down the center, and if you look down the lower at the bottom, those are actual pictures of real systems that are illustrating each one of these points. So you've got this bipolar outflow, it doesn't last for more than 10,000, 100,000 years, quick. And then you settle down and you start making your asteroids, your comets, and they quickly build up and make your gas giants, your Jupiters and your Saturns, Uranus and Neptunes that Abby loves so much. You've already made, possibly, you're also making the KBOs that Kirby liked so much and was talking about, and we're gonna go visit. In the next 10 to 100 million years, I mean, your big planets, you start making your little rocky planets, like the one we know and love and live on. And then finally, once you're done made all your planets, you take a few billion years to clean out the system, maybe drop a little bit more mass on each one of the planets, grow them up. We still have meteorites coming in every day, and our Earth is growing by about 10 to the 4 metric tons every year, but not very much. And finally, you make a mature system with leftover relic planetesimals, asteroids, comets, KBOs, and those will actually emit dust and gas into a cloud surrounding the sun, and they support it. And how they emit it and how they format it tells you a lot about where they are and how they got formed in the process of making a solar system. Next slide, please. I'm not going to dwell on this other than to say is these are other people's circumstellar disks around other systems that are nearby. These are all Kuiper belts, and they all house Kuiper belt dwarf planets, just like Kirby was talking about. The real question is, we don't know what ours looks like because we live inside it until an interstellar probe goes outside of it. Next slide, please. Keep going until we get all the literature. Thank you. So interstellar probe is basically going to take us out to a few hundred to 1,000 AU, and that's going to take us beyond the limits of this dust disk, which we think extends about maybe a few hundred AU around the sun. And we know that visible and infrared observations from the vicinity of the Earth have seen very bright zodiacal cloud, it's called, and that's mainly coming from asteroids grinding against each other in the main belt, and also coming from the occasional comet that comes by and sublimes and kicks out dust and gas. We're immersed in this very bright, very local dust disk, but it turns out from one mission called New Horizons that's now flown out through the disk and counted dust particles, we think that 97% of the mass of all the dust particles orbiting the sun right now are not in the nearby bright cloud that has dominated all our observations. They're actually in the far one created by the Kuiper belt. The second point here I already made, disks are often associated with planets, comets, and asteroids, not just by models and nice pretty pictures, but we actually see them when counting disks and counting planets. And third, as I mentioned, is that we're going to get the 3D structure. And here's some examples of some beautiful young systems in their structure. The very famous HL Tau system with the rings where you're forming planets. And the Beta Pic, which has also got rings and got a planet and some warping in its disk. You're looking at the same thing, you're looking at HL Tau, but you're looking at edge on rather than face on. Next slide, please. We know the solar system I mentioned has two, if you will, relic planetesimal populations that are today creating parts of a dust cloud. The first is the inner system, the asteroid belt, noted here in green, as I just mentioned. The red are actually asteroids inside the Earth's orbit and not in the main belt. The outer system is the second, is that those are the Kuiper belts that you just heard Kirby allude to. So those guys are also grinding and making, and they're also getting hit by dust coming in from the galaxy, which we're going to sample as well, and getting sputtered, and they're creating this giant outer disk, which nobody really knows anything about except for one measurement by New Horizons. We don't have an idea of its shape too much. We don't really know how it extends. We just have this hint. We know it's there from New Horizons. And here's the predicted morphology using the New Horizons fly-through data on the right. And we want to go out and take a picture of this and prove it's there. Next slide, please. So what we're going to do with Interstellar Probe is two things. And this is a little busy. I'm going to go a little fast here, I think, in order to make up some time. But what we can do is the equivalent of walking through a cloud or a fog bank and constantly looking in front of us and walking through and measuring how bright things are in front of us. And as you know, if you're going through the fog bank, as you get near the edges, it's going to start getting fainter and fainter till suddenly you break out of this white diffuse cloud and you can see mountains and the earth and rivers and things, and you suddenly see everything has opened up. We're going to do roughly the same thing with Interstellar Probe. We're immersed in this dust cloud surrounding the Earth and near Earth space. And as we go past 10 AU, where most of the dust is in the asteroid belt, inside Jupiter and Saturn, suddenly things are going to get a lot clearer. And as we go past 100 AU, they're going to get much, much, much clearer as we go past the Kuiper belt dust. So we're actually going to be able to do what we call tomography. We're going to continually take measurements as we're moving out through the cloud, and then we can invert them to figure out what was the brightness surrounding us as we were moving out. Next, and then excuse me, let me say here one second. Once we get totally outside the cloud, we're going to turn around and do what Abby was just talking about, is we're not only going to take a picture of the planets, we're going to take a picture of our whole dust disk. So we're going to get a picture just like some of those Hubble pictures, and we're going to combine those both together to do a fantastic suite of measurements on this giant cloud surrounding the sun. Next, please. At the same time, Interstellar Probe is most likely going to carry something we call a dust analyzer. It's going to count dust particles just like the New Horizons did. And the New Horizons data is in the bottom right of this figure, where it says asteroidal dust and Kuiper belt dust. And it's also going to be able to actually measure the chemical composition of this dust. If it has rocky atoms or if it has icy atoms, because we think it's coming from Kuiper belt objects and comets and things like that in the outer system that have rock and ice in them. If you look on the right, you're going to see the plot of the New Horizons flight path, which has been alluded to already. As it flew out from the sun, went past Pluto, is now in the heart of the Kuiper belt, and getting actually even farther past the middle of the Kuiper belt. And at the bottom are the number of counts measured by the New Horizons dust counter versus distance from the sun. If you look at the extreme left, you'll see that there's a huge spike. This is a log plot. So there's a big, big, big spike where it goes up to 10 and even 100. It's off the plot. That's the inner system dust that I talked about before that dominates everything near us. Then it comes down 5, 10-ish AU, but it doesn't come down and just kind of go to very steep decay like it looks like it started to do. It hits a plateau. That plateau is the Kuiper belt dust. That's just newly discovered by New Horizons, by one fly through of it. So this is why there's a huge opportunity space to suddenly really go to town on this incredible dust population and this cloud, outer cloud that we don't know much about. We know it's there. Next slide, please. Oh, and I should just say very quickly, we can say on the slide, is that what the dust analyzer encounter will do is, from the remote imaging we're going to get, this mapping I mentioned, doing the tomography, we're going to get the idea of the 3D structure. We're getting an idea, we're going to be able to model how many pieces of dust are along different places in this cloud by actually counting pieces of dust. As we fly out with Interstellar Probe, we're going to get ground truth along one of the chords or one of the directions through this model. And that's going to give us ground truth for the model. So it's really powerful synergy. Okay, and the next slide is talking about another piece of science we can do. Once we're outside of this immersive cloud, this obscuring cloud, suddenly the whole universe shows up, okay? Much, much better than it does at the Earth because we have stuff in the way. And as I mentioned, well, we live around a star. We know there are galaxies out there. We know there's a big bang that started the whole universe. This plot on the left, I love it because it shows pretty much everything from the dawn of time to now. And time is going from left to right. The Big Bang is that white kind of spherical glow there. That's the explosion that started everything. The primordial fluctuations are what gave us the giant superclusters of galaxies. And the density perturbations that become the superclusters. And the galaxies eventually collapse and make stars, as we know. And the stars make planets and make us and make this talk. So that's what's going from left to right. If you could click once, I think there's a little bit more verbiage coming up. Thank you. There's a lot we don't know about this process. We know pretty much a lot about the Big Bang. We know about the very beginnings of when we think all the electrons and protons came together to make neutral hydrogen. We don't know how the first stars and galaxies formed very well at all. There's an awful lot of obscuration there, especially as you can see by the zodiacal cloud. And then when the stars start first collecting, they start getting hot enough that they reionize the universe and give us the plasma-dominated universe we see today with all its beautiful galaxies and stars and superclusters, et cetera. On the right, you see is the predictions actually of all the different backgrounds, if you will, all the different contributions, everything from gamma rays to X-rays, optical light from stars, infrared from hot dust, the cosmic microwave background, the CMB, everything that was created since the dawn of time by these processes that made the universe. So if we can actually measure each one of these, we can get a very good handle on what happened in order to bring us here today. It's called the extragalactic background light. Specifically, what we can do best for Interstellar Probe is get a handles on the CIB and the optical. I'm going to talk mainly about the CIB, the cosmic infrared background. Next slide, please. So IRAS and COBE are two main missions. IRAS flew in 1983, COBE in 89-90, measured the total cosmic infrared background. So this is a picture of it. And it's dominated locally by two things. One is that since there's the galactic coordinates, the galactic plane is horizontal in this plot. It's a beautiful figure here. We live about 2/3 away out from the center. What you see kind of looks like, I don't know, a shuriken or a Z, or the kind of crossing the kind of fainter but kind of electric blue structure. That's the ecliptic plane. That's our dust cloud surrounding us. And you can see it's actually pretty bright too. What you really want to be getting is the faint black stuff and understanding what is, that's the cosmic backgrounds. We need to get outside of that electric blue color, if you will. That's the local emission in order to actually be able to do a good measurement of the faint backgrounds. So next, please. Keep clicking until you get all the, thank you. So this is another way of saying that. The plot on the upper right is showing you the red curve is what we predicted, models for what we think is all the light from all the stars in the galaxies in the universe. The light blue are the curves for the foreground, what's coming from the zodiacal cloud. And at 1 AU from the sun, where we live, 3 AU, then 5 AU, then 10 AU, you see how it's decreasing as we get farther and farther away from the sun. And once you get around 30 or 40 AU, you're below the red curve, and suddenly the foreground isn't very important anymore. And that's why we need an interstellar probe to do this problem right. The other thing I want to talk about and show is that, okay, fine, we've made this all the story, and we've got a model, so why do we really need to measure it? Well, if you look in the lower right plot, 2019 paper by Cowley et al., the black points are measurements. The curves, the medium blue curve and the dashed blue curve, blue-green curve, are models. You might notice that at 10 to the 1, so this would be, excuse me, at 10, so this is 1 micron to 2 or 3 microns. The data points are significantly higher than the models. Right now, the sky is too bright, considering all the galaxies and all the stars that we think are in it. There is tension, there is a problem. There is a fundamental cosmophysical problem that we don't understand how we got here, given all the models of how we think galaxies form and stars form and evolve. So there's some really fundamental physics, astrophysics we can do here. Next slide, please. Okay, there's plenty of other astrophysics I don't have the time to touch on. And we'll be getting off very soon. So, and I'm just going to point out really quickly, we can do exoplanet transits. We can do what Abby was talking about for solar system planets, but we can turn around and we can stare at other people's planets as they're transiting stars, if that's considered important. We can do microlensing. What we can do is we can actually watch a star go in front of a distant, very bright quasar. And it will microlens. It will use its gravitational effect, general relativity, to actually focus the light as it goes past the star. And if the star has a planet, it will also cause a perturbation. You can see little spikes in this curve here. See how it goes up toward the peak and then there's spikes. There's a star and then there's a planet. You get much, much different curves if you're far away from the Earth as if you're on top of the Earth. So what you want to do is basically get what we call a nice lever arm, or two different very unique points of view. One at the Earth could do this microlensing, another one at 100 AU from the Earth would be fantastic to get you basically stereo on a microlensing system. And we have days to weeks of advanced time to know about this. So we could actually steer on vector onto one if we got notice of one. Sorry, so I'm going to stop there because there's way much more to talk about and we need to take questions and answers. But if you like this talk, go to the next slide, please. Let me point out that there are 2 more talks that are going to go into much more detail about the circum-solar dust disk, which ground truth for planetary system formation. That's going to happen on the 1st of October of this year. And then 4 weeks later, on the 29th of October, we're going to have another talk about the extragalactic background light, all the light in the universe from the beginning of time, as I mentioned, and talk much more detail about why is there tension and what we think could possibly be the answers to that, and how Interstellar Probe can give us those answers. Finally, I only touched about it very briefly. I talked about the interplanetary dust and dust coming from solar system. The galaxy is full of dust as well. And that dust is streaming in. Some of it hits the Kuiper belt and the bodies I mentioned and makes the Kuiper belt and spalls off Kuiper belt dust into our cloud. But there's lots of very interesting dust in the galaxy, which is interesting in its own right, as well as the fact is that those were the seeds of the dust and the rocks that we have in our solar system today. So we need to understand what happened to that dust from the galaxy and how it changed over to become the dust that we know and love and the rock that we know and love today and that we live with. So these are all fantastic talks. I hope you liked what we just talked about, and I'll stop there and say thank you very much.
Okay, thank you very much to all of our panelists for their wonderful presentations. We're now going to go to the question and answer session. So I see there is one question that was asked that Kirby responded to, so we'll just kind of address that right now as a group. So Ron Ghosh asked, general question, can the interstellar probe shed any insights into the Oort cloud? Kirby, could you comment on that to the group?
Yeah, I think the short answer is probably not, but it's not outside the realm of possibility. My understanding is the inner edge of the Oort cloud may be around 2000 AU. We've been designing to something that's capable of working from 1000 AU. Now, if an Oort cloud object were knocked onto an orbit that brought it closer into the closer to the solar system, it's possible remote observations could be done, much like New Horizons is doing now with remote observations of Kuiper belt objects that give kind of rotational phase curves. That could probably, that's within the realm of plausibility. But I think really it's going to be best equipped to really look at what's happening much closer in at the Kuiper belt, which tends to run from roughly 30 to 55 AU.
Mm-hmm. All right, thank you very much, Kirby. Great, we just got another question in. Will we be able to reach the icy moons of planets to look for signs of life? So maybe Abby, you can comment on that one?
Hi, yeah. Our Jupiter flyby, the closer we get to Jupiter, the more energy we get from the flyby. So there's an interesting thought. We haven't looked at that, and now we've decided the direction that we're going out, and I think we've got a handle on the launch window that we're going to be aiming for. We could start to refine those, and yeah, even a flyby, a close flyby of one of Jupiter's icy moons would be a really valuable diagnostic, actually. And with a particle suite, if we're going really fast, one of the things that we used to our advantage at Enceladus, with Cassini and Enceladus, was that there were very high flyby speeds. I think it was like nearly 20 kilometers a second. And so when the thermal plasma gets into the sensor, it's accelerated to higher energies and actually easier to detect. So we could actually do some composition measurements because the flyby was so fast that we couldn't do with the slower flybys at Titan rather. So yeah, that's a possibility we should look at. I think looking at icy moons outside of Jupiter, I think going back to what I was saying about the auroral footprints, I think it'd be more like the signatures in the magnetosphere of the presence of that moon rather than a direct observation. That's a great question. Thank you. Think about.
Thank you very much, Abby. And the next question is for Pontus. Any thoughts on flying through the solar focus to use the sun as a gravitational telescope?
Yeah, we've gotten that question before, of course. So to give you a background of what it is quick here. So basically the solar gravity focal point is the focal point where you could use the sun's gravity as an enormous telescope, just like you use galactic gravity for seeing objects very, very far away. So when it comes to that gravity lens theoretically starts at around, I think, 563 astronomical units, and that's when the rays of the distant object touches the surface of the sun. But I think in reality, that sort of theoretical focal point that is extended really starts being effective at around 2000 AU. And that is much beyond where an interstellar probe of this concept would go. But also in terms of pointing requirements and things like this, it would be very hard to equip with an interstellar probe like this to make any valuable measurements. So there are very extreme requirements on getting measurements from that focal point. There are several papers out there that I encourage people to take a look at. There are, of course, the papers by Field of Elms, and there's papers also by Slava Turishev, who is the main pusher and analyzing this concept of measurement. So I encourage people to take a look at those papers. You feel free to email me or others, and we can sure direct you to those papers. Thanks.
Thank you very much, Pontus. The next question is, could we observe transits of terrestrial planets from this probe? So I'll hand this to Abby.
Yeah, we could. I mean, if that was our priority, we could put an adequate camera package on that we could stare directly at the sun, but it would be very, very optimized for just the observation. So that isn't the direction we decided to go. And I do think it might take, but that wouldn't be in every wavelength anyway. But like Casey was saying, we could use it to look for transits of actual exoplanets by looking out into the distant universe. So we're going to focus more on making the direct measurements of planets when they're off the limb of the sun.
Thank you very much, Abby. And the next question from Alan Stern is, an additional potential for an interstellar probe solar system science would be Centaur and possible Neptune Trojan flybys, both never explored to date.
Yes.
Yeah. I don't know if Casey, if you want to quickly comment, or the whole team. Yeah.
No, absolutely. Centaurs would be, to me, would be incredibly high priority. Just like Pluto was groundbreaking, revolutionary science going by a Centaur, which is a whole other population. We think our KBOs that are coming in to become our short period comets would be a fantastic piece of science. Never been.
Working with our colleagues with the Neptune Planetary Mission Concept Study, we came up with a list of the centaurs that trajectory could take us by, which will be adapting to look at the interstellar probe trajectory. Because very important science.
And hopefully, as Kirby was saying, there's 450 known centaurs now. Hopefully there's one along any trajectory we can pick that interstellar probe could take.
Okay, thank you very much, everybody. And trying to look at one last question. So we had, which type of probing the universe is better? Is it using the transit technique or microlensing or anything else? I'll give this to Pontus, and then if Casey wants to comment on it after that.
Yeah, I was going to throw this directly over to Casey, actually.
Okay, Casey, take it away.
Thank you. That's a huge question because probing the universe, you're asking me if there's one piece of science I would think is the most important and is motivated by our moving far away from the Earth, because I think we can do it all. If we're going to look at the Zodi cloud, we can then turn around the dust cloud around the sun. We can turn around and use the exact same instrument that we're going to use to map the surface of a KBO to get the cosmic backgrounds. It comes for free, if you will. So that's a piece of science that's going to be done, and that's fantastic. It gives you all the light from the beginning of the universe. We can also, if you will, I'm going to use the term repurpose or multitask. That same optical UViz near IR camera that would map the surface of a KBO can be used for exoplanet transits. So as we just talked about. So that's another piece of science that you don't have to, add on. It's there. If we're going to do the planetary flyby, we're going to get that for free. If we want to do the microlensing, again, we use the same sort of instruments. And if I didn't mention it, we also want to look at our zodiacal cloud, I use the terms interchangeably, the dust cloud around the sun, not just in the infrared. We want to look at it with the optical, with the same camera we're going to do with the KBO flyby. So I've kind of taken your question, not answered it exactly, because saying, should we make a new instrument to go and do this? I think I've changed the question into, we're going to get all this additional science with all these instruments if we just put a little bit of thought into making them more multidimensional, if you will, or more multitasking, and that isn't hard to do. So another thing we haven't talked about at all is there's going to be most likely a UV spectrometer on the heliospheric instrument package, which is going to do an awful lot with understanding hydrogen in the heliosheath and the heliopause. Taking that same instrument out and looking at the cosmic UV background. Remember I showed you all the different backgrounds from all the galaxies and stars from the beginning of cosmic time? We didn't talk at all, because we didn't have time, about the cosmic UV background. We're going to go to town on that too. So there's all kinds of things, pieces of science that can be done with an interstellar probe, and that are only going to build. And if we get ideas from the audience or from other people, that we can add to the, if you will, the experimental suite that we're going to take outside the solar system into the nearby galaxy.
Thank you very much, Casey. And that's all the time we have for today. Thank you very much to our panelists, and thank you for attending today's webinar. The next webinar will be on Thursday, August 20th at noon Eastern Time on Voyagers 1 and 2, Where Are They Now? Where we will have a presentation by Professor Leonard Fisk and Michael Paul. Please visit the Interstellar Probe Study website for more information about the study and to view information on future webinars and events. Also, please consider signing up for our listserv under the community involvement section of the website to make sure you are getting the latest information on upcoming webinars and events. Thanks for joining us and have a wonderful day.